Hello, everyone, and welcome to my bonus 11.6 video. Again, 11.6 was covering the ratio test. And I think one of maybe the most difficult thing about the ratio test is when you're dealing with these factorials. And so I've chosen for us, again, kind of something that's certainly on the upper end of the spectrum here as far as difficulty goes. But I don't think this is completely, unreasonable to show up on a quiz or an exam or anything like that. Again, our goal here is to determine if this series converges or diverges. And better yet, because this is an alternating series, right? We can see that we have the -1 raised to various powers. So this is going to be negative, then positive, then negative, then positive, so on and so forth, right? We learned in 11.5 that we can actually break this down a little bit farther, right? And say whether it converges absolutely, converges conditionally, or if it diverges, right? So we got this third bin kind of that we can put things into. That converges absolutely versus if it just regular old converges conditionally, or of course diverge. And so I would like to use the ratio test in order to determine what's going on here, right? Notice, by the way, that this does not say use the ratio test, right? And so thinking about ahead a little bit towards our next exam, part of this is certainly going to be, right, when you see a series like this, how do you know which of our tests to use? And so that's something that I want you to be kind of thinking about a little bit in the background here. I do have a review video coming up, especially for the exam, where we do really face, right, how do you know when to use which one of these tests? Let's again, maybe ordering sort of deal. So we are just about all the way through the various tests that we have. And so there's, certainly we have to compile all of this to, okay, we now have all these tools. How do we know when to do what? So that's certainly coming up as well. Okay, so again, we would like to figure out if this converges absolutely, converges conditionally, or diverges. I'll tell you, right, because we have these factorials here, factorials are usually a good indicator that you want to use the ratio test. So anytime you see these factorials, my claim is that the ratio test is a pretty good idea. And so let's go ahead and try to apply the ratio test here. Remember, the ratio test, it's probably my favorite test. I think it's a lot of folks' favorite tests because you don't have to come up with anything, right? First of all, there's not a lot of conditions, right? If you think about like the integral test had it to be positive, continuous, decreasing, all this sort of stuff, right? And for instance, the limit comparison test, or even the direct comparison test, right? You had to come up with these clever comparisons. You had to go out and figure out what should the B sub n be to compare with your original series, right? In order to get some good results, right? So you had to be a little bit creative with this. The alternating series test is, not so bad. It does work for only alternating series. But this one, right, you need to show that it was decreasing and that the limit was going to 0. So again, there are some conditions there. But again, the ratio test is quite nice because there's really not so much to do. All you have to do is evaluate out this ratio of subsequent terms, right? So your a sub n plus 1s divided by your a sub n's, take the absolute value of that, and you look at what that limit is, and then you get the result kind of immediately from that. So let's go ahead and do this. I'm going to do the limit as n goes to infinity. We're going to take the absolute value of, and hopefully you've done a few of these problems before, right? I'm going to go through the setup here a little bit fast, right? I'm going to do my a sub n plus 1 first. So I'm going to have -1 raised to the n plus 1. So again, everywhere I see an n, I'm going to be putting an n plus 1. I'm going to have n plus 1 factorial, and it looks like this needs to be squared. So I'm going to be squaring that. And then divided by 2 and n plus 1 plus another 1. And notice how you have to be really careful with this, right? Substituting in an n plus 1 everywhere you see an n, because there's a 2 right next to that n. And so you're going to need to distribute that 2 to kind of each one of these pieces. All right, that right there is my a sub n plus 1. Now we need to divide by our a sub n. And instead of doing that, right, instead of dividing by this fraction, I'm going to go ahead and multiply by the reciprocal. And that's what I mean by kind of, I'm going to take this a little bit faster than maybe the first time I did through this. So I'm going to divide by, so I'm going to multiply by the reciprocal. So you can see the 2n plus 1 factorial is now on top. And then in the denominator, I'm going to have -1 to the n and n factorial being squared. So that's me dividing by a sub n. But again, instead of writing that, I'm going to write that I'm multiplying by the reciprocal. Okay, now let's go ahead. And the second bit, right, that you always want to do with the ratio test is kind of combine the like pieces, and hopefully we get some stuff to cancel out. So let's go ahead and rearrange this a little bit and combine the like pieces. So maybe first of all, the first similar piece, right, we have this -1 raised to a power. And so I'm going to go ahead and put that, right, rearrange these fractions a bit. And so that I have this -1 raised to a power in the numerator, -1 raised to a power in the denominator. And these I'm going to consider as one grouping. Next up, let's think about maybe this n+1 factorial and it's squared, right? So I'm going to have this n+1 factorial. And maybe, right, it's squared, so it's just multiplied by itself. So maybe I'm going to be explicit about this, and I'm going to write out another n+1 factorial here. And so right now, again, I'm taking care of these guys. And so the corresponding piece that goes along with this is going to be this n factorial squared in the denominator here. So I'm going to go ahead and again, kind of combining these like pieces. I'm going to put one of my n factorials here. And again, it's n factorial squared. And so I'm going to put another n factorial here. Okay. And then lastly, we have this 2n+1 factorial. Okay, 2n+1 factorial here. And in the denominator, right, I have a little bit more here. I have 2 times n+1, the quantity. So if I go ahead and distribute that, I'm going to have 2n+2 plus another one here. So that's going to be 2n+3 altogether. And again, this is all inside of the factorial. This is all inside of an absolute value here. And again, kind of I've just cleverly rearranged my fractions because again, you're allowed to multiply in any order that you want. So I've just kind of rearranged things so that way I have all the like pieces together. All right, now we're going to be hoping for some, simplifying to go on here. And you'll see that there's kind of two big properties that we use, as you probably saw in the pre-class video and even the in-class video. One of them is for these exponents. So for instance, right, we see that we have -1 raised to the n+1 in the numerator and -1 raised to the n in the denominator. And so you may remember, right, if you have a to the b divided by a to the c, this is equal to a to the b minus c. So this is a property from our good old algebra days. And so if we apply that in this situation, right, -1 raised to some power divided by -1 raised to some other power, well, then this is going to be -1 raised to, and we're going to subtract, right? We're going to have n+1 minus n. And so when you have n+1 minus n, notice that these n's are going to perfectly cancel out. And you're going to be left with just -1 raised to the first power, or that's going to be the same thing as -1. So we need to remember this property of exponents. And by the way, so if you don't like remembering these algebra rules, I don't blame you by any means. You can think about this logically as well, right? Notice that we have one more of our -1s in the numerator than you do in the denominator. And so a lot of them are going to cancel out. In particular, n of them are going to cancel out. And you're going to be left with one more in the numerator than you do in the denominator. So if you just think of it literally as canceling out, like fractions do, right? That's why you're going to have one left over. -1 raised to the first power, one of them. And so that's kind of the more ad hoc way of thinking about it, or just kind of logically working through what it should be. Now, the factorials are a little bit more tricky here. You may remember from the pre-class video or the in-class video, right, that there's a way to simplify these things and get them to cancel out a bit. So I'm just going to remind us, right, that n+1 factorial, what this means is that you have n+1 times, and you kind of keep on taking a step of one down, right? So the next one is going to be n, and then n-1, and you keep going all the way until you get 3 times 2 times 1. So this quite literally is what n+1 factorial means. Now, if we were to divide this by n factorial, well, n factorial very similarly, right, is now you start at n and you just take steps of 1 down. So n minus 1, and then n minus 2, and then you keep on going all the way until you get to 3 times 2 times 1. And so you can see that there's going to be a lot that cancels here, right? The n's cancel, the n minus 1s cancel, the n minus 2s cancel, the 3s cancel, the 2s, the 1s, right? Everything in between. And the only thing that's left is just that n plus 1. And so the rule that we saw from before in the pre-class video or the in-class video, right, is that n plus 1 factorial is equal to n plus 1 times n factorial, right? And so quite literally, when you divide through by that n factorial, right, you're just going to be left off with this n plus 1. Okay, so using those two pieces of information, we can go ahead and simplify our limit considerably. So I'm going to do the limit again as n goes to infinity. We know that that first set of exponentials simplifies down just to -1 raised to the first power. Here we're going to have n plus 1 factorial divided by n factorial, as we just saw that this simplifies down to n plus 1. Again, you know, you could put denominators here if you really wanted to, divided by 1. Again, n plus 1 factorial divided by n factorial is going to be n plus 1. Ooh, and I didn't do this one yet. See, maybe pause the video for a second. Try to simplify out how can we simplify this more complicated factorial, right? Where we have 2n plus 1 in the numerator and 2n plus 3 in the denominator, and see if you can get this one. So pause the video, try to do this one on your own, and then come back and I'll show you how it's done. All right. So I went ahead and wrote out very similar to what we did for our n plus 1 factorial divided by n factorial, right? So again, 2n plus 1 factorial is going to start off with a 2n plus 1, just like I have here. Then we're going to step down by 1. So we're going to go down to 2n. Then we're going to go to 2n minus 1. And again, you keep on taking the steps all the way until you get to 3, 2, 1, however long that takes. They're all being multiplied together. Similarly, 2n plus 3 is going to be starting off at 2n plus 3. Then we take a step down, so 2n plus 2. Then we take another step down, and you keep on doing this all the way until you get to 3, 2, 1. Now notice that we're going to end up having some canceling that happens, right? Mainly, when you get to 2n plus 1, we have a 2n plus 1 in both the numerator and the denominator. And so those are going to cancel out. Likewise, the next one would be 2n, right? And this is going to cancel out. And we're going to keep on canceling until we get to canceling our 3s, our 2s, and you don't really have to cancel those 1s, but fine, we'll do it, right? And so we can see that there's going to be a lot of stuff that cancels out. And the only stuff that's remaining is going to be this 2n plus 3 and this 2n plus 2 in the denominator. Everything else cancels out. All right, so we have simplified down quite substantially here. The last bit, right, maybe we can apply this absolute value. We could have even done it earlier if we wanted, right? And the absolute value is really only going to affect this negative right here. All of these other things, right? Remember, n is going to infinity. N is going to be a very, very large positive number, something like 1,000,000 or 1,000,000,000 or 1,000,000,000,000, right? And so all of this stuff with n's is going to already be positive. The only thing that's negative, the only thing that the absolute value is really influencing here is that -1. And so let's go ahead and apply our absolute value here. And I'm going to simplify things down a bit more. So I'm going to write n plus 1 here, n plus 1. That's all the stuff in the numerator. And then in the denominator, I have 2n plus 3 and 2n plus 2. And so, yes, things have, simplified down quite substantially now. And now we're kind of safely back into our Calc 1 days, or even, we could do our Calc 2, right, our L'Hopital's rule sort of deal, right? Because if you go ahead and you try to plug in infinity, you'll see that you have an infinity over infinity indeterminate form. And so let's go ahead. There's several ways that we can go about solving this, but I'm going to go ahead and expand out these polynomials in both the numerator and the denominator. So if I FOIL out in the numerator, right, the firsts N times n is n squared. The inners, 1 times n is going to be n. The outers, n times 1 is going to be n. And the lasts, 1 times 1 is going to be 1. Of course, you can combine like terms. So instead of writing n plus 1, sorry, n plus n, you could, of course, write 2n. And similarly, if you go ahead and FOIL out in the denominator, we're going to have 4n squared. Let's see, 6n and 4n is going to make 10n, and then 3 and 2 is going to make 6. So I did that one a little bit faster there. I write it like this because this is really nice to take derivatives of, right? And by the way, there's lots of ways. Once you get to a situation like this, some of you may just look at this and say, oh, I know the answer is 1/4. Because I remember back from our algebra days, right? If you have these polynomials with the same power, well, then the end behavior of this function is going to be a horizontal asymptote, right? Where the asymptote is at this ratio of leading coefficients, right? So you're looking at kind of the 1 here and the 4 there, and you might be able to get it that way. Some of you may like the Calc 1 way of solving this, right? Where you divide through by this highest power in the numerator and the denominator, in this case, n squared, and that would be a fine way to do this. Or some of you may like L'Hopital's rule, right? So you could apply L'Hopital's rule twice in this case. So if I did L'Hopital's rule once, I'd have 2n plus 2 in the numerator, and then 8n plus 10 in the denominator. If you plug in infinity over infinity, right, you're going to have another indeterminate. It's going to be this infinity over infinity situation. So you could apply a L'Hopital's rule one more time. And when you take the derivative now, you're going to get 2 divided by 8, which is again 1/4, right? So there are lots of ways to go ahead and evaluate this limit once you've gotten to this point. Okay, so the last big thing here is we get this result of 1/4. What does that mean, right? So each one of our tests, right, the conclusion, right, is different based on what you get for these limits. So for the ratio test, you know that if you get this limit that is less than 1, that's the big condition here, less than 1, then our series converges absolutely. So that means our original series that we have up here converges absolutely. And so we're done, right? That's all there is. It converges absolutely. We've won the game, and that's our final answer. But you can see that, again, kind of dealing with all of this algebra, right? All of this kind of writing out these crazy fractions, the exponentials, the factorials, all that sort of stuff. You can see why this is on the upper end of the spectrum, right? This took some work to kind of get the final result. All right. Thank you so much for watching, guys. I hope you have a wonderful day, and I'll see you out there.